And so here's a video for week 6 notes, ionic and covalent bonds, molecules and compounds. The test though is 10/17, so this Thursday. This is just a list of some cations or some metals, and we have group 1, group 2. Beryllium you don't really see, but you might, so I would just for now just write +2. Selenium, it says it's always a +3, but that's not something that we've covered or is in ALEKS. Zinc is a +2, silver is a +1, aluminum is a +3, and sometimes you do see those elements showing up as +3, so this really isn't the best graph. Just go with essentially what we've been saying. Now, an ionic compound is between a metal and a nonmetal. So we have these right here, essentially to the left of the metalloids, and these over here to the right of the metalloids. And could be between a cation and anion, a metal and a nonmetal. And keep in mind, well, hydrogen doesn't really come up. Left of the periodic table and right of the periodic table. This is a good song from my childhood. Still remember every word. It teaches us about how opposites, cation and an anion, attract to each other. It's like opposite magnets. And just like Paula Abdul likes to wake up early, and the dog, so she's in the video, she's attracted to, I guess, a singing dog or something. And she likes to wake up early and she likes to stay up all night. She likes movies and the dog likes TV. And so cations lose electrons, anions gain electrons. Both have a full octet, aka the meaning, blah, 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 and they can attract to each other. So here we see, and there should be a negative charge in there. Here we see sodium has 1 valence electron, and chlorine has 7 valence electrons. Sodium wants to form a +1 charge, chlorine wants to form a -1 charge. So sodium's electron, 1 valence electron, goes to chlorine. Chlorine now has 8 valence electron. Sodium, underneath that 1 valence electron, has 8 valence electrons. Now that they are oppositely charged, they're going to attract to each other. And they both fulfill then the octet rule and become like a noble gas. Now here we see that with lithium. Lithium is a group 1 alkali metal. It's 1 valence electrons. Wants to lose 1, fluorine wants 1, and that's why we form lithium fluoride. So the reason why I made this slide is lithium underneath that has 2 valence electrons. So things like in period 2 or hydrogen later on with covalent bonds, 2 is enough because helium has 2, and helium is a noble gas. So here, when writing the formula for ionic bonds, I sort of just jumped into practice questions, and just because that's just the way I think it's a good way to learn it. Aluminum we know is in group 13. Oxygen we know forms a -2 charge, and they bond together. We need 2 aluminums and 3 oxygens to create a neutral charge, so that's going to be Al2O3, and that, just for future reference, that's going to be aluminum oxide. So we have to Here it's being asked like the dissociation equation for aluminum oxide, Al2O3, and it's a solid, as you saw in lab. It's a solid, it looks like a salt, and if I said to an adult or something, do salts dissolve in water? And they would say, yeah. And so most do, some don't, but it's but again, what we're looking at right now is we're going to just assume they dissolve in water. And so you did see that one magnesium oxide not dissolve in water, but some did. So all salts do slightly dissolve in water no matter what. Most completely dissolve in water, but that's not something that matters right now. It becomes aqueous, and this is what it is. And so keep in mind that's not diatomic. Like a student asked, well, there's O2 floating around in water. Wouldn't they want to bond and form the diatomic? And at the time, I really wasn't sure on how to answer it. But at this point, they already have that full octet. Hence, they would not bond and form the diatomic because as O2 minus already has that octet. Wish I had that because it gained 2 electrons. I wish I had that answer at the time, but I just told the student to sit down and be quiet. Here we got calcium 2 plus, oxygen 2 minus. There's the same charge, so it's just going to be CaO, calcium oxide. And dissociation reaction, CaO. It's a solid, Ca2 plus, Aq plus O2 minus, Aq. Now we got to write some ionic compounds. We got zinc, vanadium, fluorine, sulfur. So it says what we got to write 4. So zinc, I'm gonna try to remember those. So we got zinc 2 plus, vanadium 5 plus, fluorides would be F minus, sulfur 2S minus. I think students understand this pretty well. F form 4, Alex sets it up like a sort of like a Punnett square or like a little graph. I think that's a good way to do it. But so if you do it that way in the test, that's fine. So like zinc and fluoride are going to bond together. So it's just going to be ZnF2. Now, I hate teaching the crossover method, but it works. And then zinc and sulfur, ZnS. Then vanadium. Keep in mind the positive always goes first. So cation first. Now, would it be nice to let the anion go first sometimes? Yeah, but you know how cats are. They don't mess around. So then we got zinc sulfide, and then vanadium. Just for later reference, this would be what? Vanadium 5, well, it tells us the charge right there. So it'd be vanadium 5 sulfide. We got those 4 right there. So cation first. And here's some practice answers. You can also practice on Alex, obviously. All right, write the dissociation. I did this too much. I don't know. I'm trying to think of what. Maybe on the last. I'm just gonna write one. So aluminum. I'm gonna write the hardest one. I might be wrong though on what. What there's aluminum sulfide maybe. Solid. It's gonna break down to 2 aluminums. We have the charge there of what aluminum is, and 3 sulfides. Sulfur ions. So it bounces. It goes to an aqueous. It dissolves, and there it is. All right, so here you have to use, essentially for all these, other than zinc, zinc is always a +2. The other three, you have to use the second element. So here, you have to use the anion to determine cation charge. So iodine is a -1. There's two of them. So nickel has to be a 2 plus. So why don't I try it this way? I think this is a good way. If I just write the anion charge for each of these by looking at the periodic table, all of these are halogens, meaning they all form a -1 charge, other than oxygen is a 2 minus. And because of them all forming a -1 charge, then we can determine the cation's charge based on the fact that it needs to neutralize the amount of anions it has. So Au gold that has a +1 charge, and since there are two fluoride ions, iron, Fe is iron, +2. So here's just another example. Let's see if there's any tough ones in here. Really, sulfur is a 2 minus. So all these anion charges we're going to know. So when you get these, you have to determine the cation charge based on the anion charge, because all these, so something, oh yeah, well, something I'll mention something else later. All these are in that transition metal area, or that group 14 area. However, silver, Ag, so Ag, I like your silver on your chain or stuff, then we know that's a +1, and that would make sense. That's why there's two Ags, because sulfur is a -2. So yeah, no more of those. All right, so naming compounds, naming ionic compounds, so a cation and anion. It's essentially the name of the cation and then the name of the anion ending in "ide." And for simple binary, so just two different elements, there might be more, but for example, like AlF3 is a binary element. That's still binary, and it follows these rules. So repeat these to yourselves a bunch of times: fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, phosphide. So I will take off. I mean, I will take off some points if it's, or like partial credit if it's not the same. Other than fluoride, I always spell fluoride wrong, so I can't take off points. I don't know how to spell it. I always spell it Flourid. The rest are pretty good. The rest aren't that bad. And then we're going to do more difficult ones later, where the cation um, has multiple charges. And so if it has one charge, or if it's a +1, then if it's a +2, then we write Roman numeral 2. I don't think I'm spelling Apollo Creed right. If it's a +3, we write Roman numeral 3. And if it's a +4, we write Roman numeral 4. You can also have a +5 and a 6. and a 7. And I don't know, you're not going to know. That's why. Okay. So these are just some examples. We can see the charge matches the Roman numeral there. These are just some of them that will do that. Okay, so here, name the compound. So if you know the charge, then know Roman numeral. We know, so look at your periodic table, calcium's in group 2. We know the charge. So it is calcium bromide, IDE. Compared to this one, PB, that's in group 14. We don't know the charge. We don't write anything at the top of that carbon. We don't know, then we need Roman numerals. Chlorine is a -1. We have 4 of them. So lead has to be lead 4 chloride. I'm going to do one more, and then it's something that you practice yourself. Lithium is a +1. We know the charge, so no Roman numeral. Iodide is a -1, Li, and then iron 3. So we don't know Fe's charge, so that's why we have a Roman numeral. Oxygen is -2, Fe2O3. So here we have some good practice. If you know the charge, no Roman numeral. So here, rubidium, group 1, magnesium, group 2, we know those charges, so no Roman numeral. R, B, C, L just cancel each other out, so that is just rubidium chloride. Just like magnesium chloride here, but MgCl2. Then copper 2, so this is CuCl2, but then we have to write copper 2 chloride. And then that one copper 1 chloride. So just for practice here, cesium, we know the charge. Calcium, we know the charge. Like cesium is just not an element in the first 20. So none of the first 20 that you did memorize will have a Roman numeral. We're going to look at polyatomic ions. These are going to be cations in them. So like nitrate, this is a anion. Oh, I think I said they're going to be cations. So there's only one cation, NH4+, and I think one other one, H3O+, that's going to be on the given CTU. But look at how the bond here between these two are covalent and molecular because they're both elements are on the right side of the periodic table, but it's still an ion. So more than one atom ion. So these will be given to you, but just some things to note, like carbonate, you're going to hear all the time. Nitrate, you're going to hear all the time. Phosphate, you're going to hear all the time. Ammonium, you're going to hear all the time. Hydroxide, I mean, all these here, you're going to, not peroxide. I mean, that's, I don't know if you're going to get any peroxide ones on the Alex, maybe you did. Cyanide, all these are pretty familiar. The weirdest one here is this acetate one that I wish the world could agree on, but that it could be written either way. If you look at it, it's the same amount of carbons, hydrogens, and oxygens, and the same charge. So I prefer C2H3O2 minus just because I'm better at remembering it. Every time I have to write the first way, I sort of, it takes me a couple seconds, but you can write it either way, it doesn't matter. Again, some common ones. All these are pretty common, that, if you take more chemistry or even in biology, it comes up quite often. And in everyday language, when they're talking about science, you hear sulfates and nitrates and all that stuff. So you hear these words here and there. So I'll do one example. Oh, whatever. This is easy. I'm not going to do these. So yeah, you just got to match these with the polyatomic ion. So here's just an example. We name. This is how. Just some rules from the book that you can use. This is something that is going to get students. If you know the charge, know Roman numeral. PB, group 14, not in the +1, +2, +3. So, well, first let's write the empirical formula. So this is, makes that easy, NH4, ClO3, PB, CrO4, Cr3, PO4, 2. So I think, if you don't know those, definitely work on those ASAP. And then this top one, we know the charge of NH4. NH4 is always +1, and it's ammonium. And then chlorate. We do not change the name of a polyatomic at all. So that name stays the same. Maybe think, okay, well, something's easy about the polyatomics. We don't change the name. Here, lead, we do not know the charge. It says +2, but we don't know it. So this is going to be lead 2 chromate. Nope, lead 2 chromate. And same with chromium. We don't know the charge of chromium. So again, look at the periodic table, and that is chromium 2 phosphate. So now we're looking at molecular and covalent bonds. So these are bonds between two nonmetals, or a metalloid and a nonmetal in some cases. So things essentially to the right of the staircase, and a metalloid. And I think most of you know where metalloids are. If you don't, watch a previous video or look up metalloids. And I definitely want you to know, those major 6 that are in periods 1 through 5. So they share electrons. It's between two nonmetals or metalloids, or a metalloid, or semi-metal, whatever. I forgot. I always forget how I taught it. And we'll do the sharing electrons later. So here, prefix, name a first element, prefix, name a second element, ide. So these again are diatomic ide. I don't know a good way to remember it because students forget it all the time. So if it's di, meaning just 2 elements, the word backwards is ide. So yeah. So, but these prefixes you got to know, but nothing too tough. Name each compound. First one's going to be, so you don't use mono if the first one is 1 first. And the best way to remember that is CO2 is carbon dioxide, CO is carbon monoxide. So we got nitrogen, triiodide, phosphorus, pentachloride, tetraphosphorus decasulfide. So here, predicting whether it's ionic or covalent. So between one of these and one of these, it is ionic because it's ironic that two opposite things are attracted to each other. Now, in chemistry and physics, that's true, or it's not ironic, but let's just say it's people. And then molecular, it's between two things on the right, often silicone, AS, sometimes boron, and then the nonmetals. Here, we know this is molecular, two things on the right, magnesium on the left, sulfur on the right. Nope, ionic. This one. HBr is molecular because H is a nonmetal. Review, so just work on the Alex. You have moles, you got to get to grams, multiplied by molar mass, and just remember fluorine is a diatomic, it's a gas, so when, let's say if it's NaF, it's not a diatomic, so when bonded, and then also when it's aqueous, it's not a diatomic. But when it's alone in its normal state, such as a gas or liquid or solid, it's going to be diatomic. This again is review, find the molar mass of something, practice it on Alex. What I would do is add up the elements. I'll change this to C2H6O, add them up, and it says 2 decimal places, which is right because the periodic table that you use has 2 decimal places, and when you add numbers, you go with the least amount after the decimal. So mass percent, again, you can practice that on Alex. Now it's sort of rational. I'm just going to do one that might be easier than the book one, but then you can practice on Alex. So if we had, let's see, just do like Mg O or something. Yeah, because you made magnesium oxide. You made magnesium oxide in lab, so that's 24.31 grams. Then oxygen is 16.00 grams, and so we got 40.31 grams. And so the mass percent of magnesium is going to be 24.31 divided by 40.31 times 100, and you're going to get the percent. Now, that's for magnesium. If you wanted the mass percent of oxygen, it's going to be 16.00 divided by 40.31 times 100, and you're going to get mass percent of oxygen. So really, what percent of a compound mass-wise is the element? So now we're going to kind of valence electrons to determine Lewis structures. And again, we see helium has 2, but otherwise it's 1 through 8. And counting valence electrons is pretty easy, but remember, if it's negative, we add a electron, and when it's positive, we lose an electron. So I'll do one that we didn't do in the class, H3O plus. Hydrogen has 1 valence electron, there's 3 of them, plus 6, that's going to be 9. It loses 1 electron because it becomes positive. So like when my ex-girlfriend dumped me, she lost something negative in her life and she became positive. So we have 9, we subtract 1, 8. So you're always going to have an even amount of valence electrons. So if you end up with like 9, look to see if it is a polyatomic ion. Molecular bonds share electrons to fulfill their octet. Ionic bonds do not. There's a transfer of an electron. molecular bonds or covalent bonds or things to the right of the staircase on the periodic table. Look at how fluorine shares 2 electrons, and if you count the outside, there's 8. H2O, hydrogen has 1 electron, oxygen has 6 valence electrons. Therefore, hydrogen's happy as helium, then oxygen has 8. Now CO2, we're going to learn this with Lewis structures. I think the first example we do is CO2. This is the same as this. Carbon now has 1, 2, 3, 4 8 valence electrons, as you can see here. Oxygen is 8, oxygen is 8. Knowing that a bond is the same thing as 2, and 1, 2, 3, 4. A double bond is written as 4. So sometimes students prefer to write it like that. I've never taught it that way, but I have seen students write it like that, and that is acceptable even on like standardized tests and so forth. So I'm going to teach this a little bit better than I did in class. I didn't do a great job. So I'm going to do these two. So we got that H3O plus, like this. And notice, since it's a charge, it has brackets and a charge written on it. So first, let's count valence electrons. We have 3 hydrogens. Hydrogen has 1. And there's 3 of them, so that's 3. Oxygen has 6. And there's 1. 6 of them, that's 9. It's positive, so we subtract 1, so we have 8. So let's count valence electrons connected to that oxygen, knowing that one bond is 2 electrons, 2, 4, 6, 8. So it fulfills the octet. Or no, it has the right amount of valence electrons. Then let's look at everything and make sure that hydrogen has 2 and oxygen has 8. Hydrogen has 2 because the bond is 2 electrons. Each hydrogen has that. Oxygen has 8. So I forgot what the other one was. I think it was something like this. HCN. And then maybe there's 2 electrons here, I forgot. But even, it doesn't matter. So count valence electrons. Hydrogen has 1, carbon has 4, nitrogen has 5. So that adds up to 10. If we count valence electrons on the thingy, 2, 4, 6, 8, 10. So that's 10. So that is good, meaning we don't dot that one. However, let's see if it fulfills the octet and duet rule. Hydrogen's touching 2, so that's things happy. Hydrogen or carbon is touching 2, 4, 6, 8, so that thing's happy. But nitrogen's only touching 6, so that thingy is sad. And so that's not going to be a compound that forms, as carbon will, or nitrogen in this case, will pull over 2 electrons, and it will be HCN. And this is one of the favorite electron structures. All right, so Lewis structures. I will do these Lewis structures for people here. So CO2, and this is just how I word it. CO2 count valence electrons. Carbon has 4, oxygen has 6. 6 times 2 is 12 plus 4, so we have 16 valence electrons. Now, the first non-hydrogen, or the least electronegative, is the center atom. So that is carbon, bond outside atoms using 2 electrons. So I used 4, I got 12 left. Make outside atoms happy first. Minus 6, I got 6 left. Minus 6, I got 0 left. Carbon needs to be happy, so make double bonds to make carbon happy. This and this. Now note, if you play with it a bit, you could technically do this and it would fulfill the octet rule. You tend to want to make it symmetrical due to something called formal charge. However, formal charge is, we're probably not going to get to it before the test. But hence, I would take this bottom one as well. You can, if you counted through it, it adds up to the right amount of valence electrons, and all the octet is filled. So now NH3, nitrogen is 5, hydrogen is 1 times 3, that's 8. Bond outside atoms using 2 electrons. 8 minus 6 is 2. Try to make outside atoms happy first. They're happy, so make center atom happy. Minus 2, 0. Fulfills octet rule, everything's happy. So CO, carbon has 4, oxygen has 6, that's 10. Let's just bond the 2 using 2 electrons. Minus 2, we got 8. Make outside atom happy first. So I would pick one atom to make happy. We got 2, make other atom happy. Minus 2, we got 0 left. Carbon's not happy, so it's going to pull over electrons. So if I do this step by step, there, still not happy, pull over 2 more, there. We got CO. We used up, we have 10 electrons, 2, 4, 6, 8, 10, and everything's happy. Triple bond is essentially like this, 1, 2, 3, 4, 5, 6. So we could write it like this, 8, 8. So H2CO, this has 4 plus 6 plus 2, because hydrogen is 2. So that's 10, 12, carbon, oxygen, hydrogen, hydrogen, bond outside atoms. What is this, 12 minus 6, make outside atoms happy, minus 6, 0. Carbon's not happy, so it's going to pull in 2 electrons, like that. And H4 plus, nitrogen 5, hydrogen 1 times 4, that's 9 minus 1, 8. Positive charge. Brackets, nitrogen. Found outside of atoms using 2 electrons. Minus 8, we used up all 8. Nitrogen's happy, hydrogen's happy with 2 electrons. ClO minus, Cl has 7, oxygen has 6. So minus 1, we're going to add 1. So that's 13, 14. Cl bond using 2 electrons, minus 2, that's 12. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's all 12 electrons are used up. Brackets because it's a minus 1 charge. All right, new structure for ozone. This one's a little tougher. Ozone is O3. That means we have 18 valence electrons. 1, 2, bond atoms together. So we used 4, we got 14. Make outside atoms happy first. Minus 6, we got 8. 1, 2, 3, 4, 5, 6. Minus 6, we got 2. Make center atom happy. Minus 2, we got 0. So oxygen is not happy in the middle. The outside atoms are happy. So oxygen is going to pull over 2 electrons right there. And that is ozone. And you can pull over any 2 electrons. You can pull over the top ones, bottom ones, right ones. They're actually all in the same place. If I'm sure that doesn't make sense, but it will soon. For butane, so this you're going to work on Alex, and I'll give you the formula. So butane, that's in like lighter, or in, with cigarette lighters, or I forgot. Lighters, I guess. So C4H10, count valence electrons. Carbon has 4, so 16. Hydrogen has 1, that's 10. We got 26. Now, when we have a carbon structure, the carbons all bond together. That's a center atom, hence all those are the center atom. So I'm going to bond them together using 2 electrons. So 2, 4, 6, and a 6, we got 20 left. And then hydrogens, I'm going to bond using 2 electrons. And keep in mind there's only those places to go. And I bonded all 10 electrons, or I bonded all 10 hydrogens using 2 electrons, minus 20, we got 0. everything follows the octet rule. All the hydrogens are happy with 2. Carbons have 8. So that is the stable Lewis structure for butane. Lewis structure for oxygen. Formula will not be given. That is because oxygen's a diatomic. 6 times 2, that's 12. Oxygen, bond them together, minus 2, we got 10. Again, I think making one side happy first is easier than like sort of even them out. So we got 0, but we used up all 12 valence electrons. The oxygen on the right is not happy, so it's going to pull over 2 electrons, and that is O2. Both oxygens are happy. The oxygen on the right suffers a little bit of anxiety and so forth, so it's not as, but that's, that's not part of the test. Nitrogen, I guessed that I was going to do this next, even though, okay, anyways, nitrogen has 5 valence electrons times 2, we got 10. Nitrogen bonds with each other, minus 2, we got 8. Make one atom happy first, minus 6, we got 2. Try to make the other atom happy, minus 2, we got 0, 0. So the nitrogen on the left needs 8, so it's going to pull over 2 electrons first. Now it has 6. It's going to pull over 2 more electrons. Now both have 8. 8, 8. So we're just not going to get to acids. So everything here from slide 105 to 112 is not going to be on the test. Again, this will not be on the test as polyatomic base, sodium hydroxide, NaOH. Drawing the Lewis structure would not be in the test, but if I wrote sodium hydroxide, you would have to be able to write this, and just for, I guess, one last time. This is a base, anything that ends with OH. Not anything, but for now. We'll cover that in a long time, though. The dissociation reaction. Not on tap. All right, so, yeah, we'll practice Lewis structures. I guess that's his nose. We'll practice Lewis structures this week. And I think naming. So what's the name of this? That's zinc carbonate, because we know zinc is a +2. Then if we go AuCO3, this is gold 1, nope, gold 2 carbonate, because carbonate, this carbonate is a 2-. All right, I hope you had fun this weekend, and